Good. Okay. Thank you. Ooh. All right, did I get it, everyone's? Okay, well, what'd you think? Huh? Shall we go over it real quick? The first one was, what is the limit as you approach -3 from the left-hand side, right, because it had a little negative on it. Do you want me to show the problems, or can I just go over them? Just go over them? Okay, so the first one was the limit as x approaches -3 from the left. So what is it? 1. You're coming in like this. Even though there's a circle here, right, open hole, we're approaching a y value of 1. So the answer to the first one was 1. The second one was approaching -3 from the right-hand side. So now we're up here, right? And we're coming in, and we're approaching, doesn't matter that there's a dot there. We're approaching a value of 3, right? So 1 and 3, and then let's see. Part C was, what is f of -3? So we wanted to know the value of the function at -3. That's an algebra question. So what's that? 3, right? So you go to -3, you look for a solid dot, you have a solid dot of 3 there, right? So the answer to the third one was 3. Part D, what is the limit as x approaches 0? And it didn't say which side, right? It didn't have a negative or a plus, which means you have to approach from both sides. And as we approach 0, where does this function go? -infinity, right? It goes to -infinity. If y'all are just coming in, y'all missed the first quiz. So, just to let you know. Got to be on time. Let's see. The next one was, what is f of 0? So what is the value of the function at 0? That's an algebra question. Do you see a dot? Go to 0. Do you see a dot anywhere? Okay, so we say undefined. Okay, undefined. The word undefined and does not exist are going to be considered two different things in this class. Undefined is what you say when you're asking the algebra question. What's the value of the function at a point? Undefined. If you're talking about a limit, and the limit doesn't exist, you say does not exist. Now I won't count off on this quiz, but do you understand the distinction between the two? Undefined is only when you're evaluating a function at a point. Does not exist is only when you're talking about limits. Yes?
So for the last one, was it undefined as well?
Let me see. So the next one was the limit as x approaches 2.
Oh, I meant the one before.
I have no idea what happened there. Okay. Oh, that was weird. Okay, what now?
The one before, the one that you just went over, was it also undefined?
At -3?
No, it was approaching 0, I believe.
When you, the limit as you approach 0? Well, as we approach 0, where's our function going? -infinity. So that's the answer that I wanted. Now, if you put does not exist or undefined, I'll probably let it slide on this one, only because in the textbook, they don't talk about infinity and -infinity as being an answer yet. Okay. They say it doesn't exist, which I completely skip over because in the next section, they're going to say it's infinity or -infinity. So I just get right to that. So if you did that, that's okay. All right, so the next one was, what's the limit as x approaches 2? And I didn't say left or right, right? So where's the function headed as we approach 2? Well, from the left, it's headed to 2, and from the right, it's headed to 2 as well. So the limit as we approach 2 is 2. And then the last question was, what is f of 2? What's the value of the function at 2? 1. All right, so that was it. I really wanted to give you that quiz just to kind of give you an idea of the expectation, right? We covered this last class. I expect that you understand it, right? So when we come in the next class, you should be able to demonstrate that you understand it. Okay, we're going to move on. Any questions? All right, let me pass around the sign-in sheet, even though I gave a quiz. You can try and get in the habit of doing that. And what are we doing today? Calculating limits. So let me bring up the notes here. I'm going to close this out. Just in case you're wondering why I'm going to put this up every class, it's so I can focus my camera, and then I lock the focus. That way when I'm walking, it's not trying to focus on me and then the board and me and the board. Just if you're curious why that's up there. Right, so last time what we did, right, is we looked at limits visually, right? It was a very visual idea. The limit, we looked at functions coming from left and right. And at the very end, I didn't put this on the quiz, but it will be on your exam, is a problem where I give you all the conditions and you draw me the picture, right? I didn't do that because it would have taken too long and I wanted a shorter quiz. So that's what we did last time, the limit of a function, just getting the idea. And now we're going to talk about 1.4, calculating limits. So this is me basically saying the same thing. We've just seen how to do things visually, but we're now going to see if there's a way that we can calculate a limit. Oh, I forgot to look at the graph of that one. Can we wait on that? Do it at the end? Okay. Try and remind me though. We're now going to talk about how we do limits if we're just given the function, not the picture, right? We're given the algebraic version of the function, or the function expressed as, you know, letters and numbers and square roots or whatever it may be. Can we look at that and find the limit without having to refer to a graph? So in order to do this, we are going to use what are called the limit laws, all right? The reason why it's all choppy here, the words skip in their spaces, because on different projectors, things project differently. So like if I zoom out, it's the way it's supposed to be. It looks all nice and neat. But to zoom in so you can see it, things look all out of place. Do y'all know what I mean? Can you all tell what I'm? All right, it bothers me, but I'm not going to fix it. All right, so we have, first of all, what are called the limit laws. All right, so when I say limit laws, what I mean is this. There are certain rules that we can apply when we're doing limits. Okay, looking algebraically at a function. And these rules, I'm going to give them to you, but I'm not going to prove to you why they are true. You're just going to take that on faith. All right? It's beyond the scope of this class to prove the limit laws. If you're a any math majors? No? Okay. I have 2 in my other class, so if you're a math major, you have to go back and do all of this again and like actually prove the limit laws. Here, we're just going to take them on faith. So here's what the limit laws say. There's a bunch of them. First, we have to suppose, we're going to start out by saying, hey, let's let C be a number. Imagine that C is a constant. C is just some number. We don't know what it is, all right? And let's suppose that we have 2 limits. I'm going to write these on the board over here on the side. We have the limit as x approaches a of some function f, and we have the limit as x approaches a as well of g of x. These limits exist. What I mean by that is that if we were to draw those functions, I'm going to do it over here on the side. Let's say I were to draw the function f. Okay? Let's say that's the function f. And I go to the point A, that whatever's happening here, this limit, as we approach A from both sides, it's headed to the same place from both sides. Right? That's what it would mean for this limit right here to exist. It means from both directions at A, we're coming into the same place. Y'all following that? Hello? Yes? So would it matter if I put an open circle here? Would that limit still exist? Yes. That limit would still exist, right? Because from the left and from the right, they're headed to the same place, right? So we are starting this whole thing off with the limit laws by assuming, right? We're assuming that this right here, all of this is true, all right? So suppose you have some number that you don't know what it is, okay? It's just some number. And that you have this limit of this function f exists, and the limit as x approaches a of some other function g exists as well. Meaning, if I draw g, that's g. Do you all agree that the limit as x approaches a for the function g also exists? It's some number. I don't know what it is, right? But it's some. We get an answer for this one. We get an answer for this one. Yeah? Y'all are giving me a look like I'm in the wrong class. Are you all right? Y'all have to give me some feedback, because this is not the type of course where you can just be like, I'll figure this out later. Ask questions. No? All right. Okay, so we have, that's our assumption. Let's start with that. We've got a constant. We've got two functions that when you take their limit at a, you get an answer. What does the first limit law say? The first limit law right here says that if you want to take the limit as x approaches a of the sum of those two functions. So if you want to add, if you have two functions being added together and you want to take their limit, this law says that you are allowed to split it up into two limits. All that means for you is this, that if you have something, has two things being added, and you want to know what happens as x goes to a, you can look at them individually. You're allowed to do that. Does it make sense that that should happen that way? I mean, like with addition, we can deal with each one separately. Yeah? You'll have to see this as I do examples, but the law is at least establishing what is okay and what is not okay. So it is okay to look at them individually. The second law says if you have two functions being subtracted and you're trying to find the limit, that you can separate them and do them individually as well, which is nice because it allows us to kind of like divide up the problem into separate pieces. The third limit law says that if you take the limit as x approaches a of c, now remember c is a number in front of a function, that what you're allowed to do is kind of ignore the number. You can kind of ignore it, put it out front. This is going to become a multiplication there. Okay, that's multiplication there. So instead of looking at c times the function and figuring this out, ignore the c and just look at the limit of the function, and then whatever that answer is, multiply it by c. So the constant can be factored out, is basically what the third limit law says. All right, the fourth limit law, and I'm going to put a little asterisk next to this because this law is nice, like it's a nice law. But as we move on this course, we're going to do something, I'm sure some of you have heard of this. This class is about something called taking the derivative or differentiation. Have you all heard that? Anyone who's talked to anyone who's taken Cal 1, it's all about this thing called the derivative. This property right here, later on, doesn't work this way. It works for limits, but it doesn't work for derivatives. And that's what makes calculus hard, actually, you'll see. But for now, if you have a limit, and notice these are two things being multiplied together, the limit law says that you're allowed to look at the limits individually still, and then multiply those two answers together. It's hard when you look at these laws, if you're sitting there going, what the hell is he talking about? Just, I'm establishing the laws, then I'm going to do examples. And when I do the examples, I'll refer back to the laws, and it'll all start to, I think, make more sense. So this just allows us to take a product and split it into two limits. The fifth law says if you have a quotient, right, division of two functions, and you want to know the limit, that you're allowed to look at the top and bottom separately. Again, take the limit of the top, limit of the bottom. You're free to do that. Now there's one condition where this would be a problem, and that's if this limit on the bottom is ever 0, that's a problem, right? Because you'd have division by 0. So this law works so long as the bottom doesn't go to 0. All right, the sixth limit law, there's 18 limit laws. No, I'm kidding. I think there's 9. Hold on, let's see. There's not that many. 9, 10, 11, sorry. So it is a lot, I guess. You don't have to memorize these. They'll become automatic, don't worry. Limit, x approaches a. If you have a function and you raise it to a power, what you're allowed to do is actually just do the limit of the function first, figure out that answer, and then raise it to the power. So it's like you're allowed to go inside. Let me give you an example. Let's say we had a function like this. If I wanted to know the limit of this function, if approaching some value, what I could do is ignore the 7, see what's happening here. Whatever that goes to, whatever the limit is of that, I would just then raise that answer to the 7th power. So I'm allowed to just kind of like focus in here instead of focusing on that. That's what this law says. All right, the 7th limit law says the limit of a constant is a constant. The limit of a constant is a constant. So this one, I think you can maybe deduce this if you just think about it. Imagine that's a number, okay? So let's say that's the number 4. And I ask you, hey everyone, what's the limit? What happens if I let x go to 2 on that function? Well, graph the function. What does the graph of this function look like? What does the constant 4 function look like? F of x equals 4. If I ask you to graph that, what is that? It's horizontal line, right? So if I graph a horizontal line like this that goes through 4, it doesn't matter where you go. Go to any place on anywhere, right? Let's say go right there. And then tell me, right here, what is it approaching from both sides? It's approaching 4, right? That would happen anywhere I go, right? It's approaching 4 from both sides because it's a flat line. So this is just saying that the limit, no matter what you ever approach, the limit of a constant will always be a constant, that same constant. All right, this next one says that the limit as x approaches a of x itself is a. So think of it this way. This is x, right? This is x. And what I want to know is what happens if I let x go to a. So what happens to x if I let it go to a? What does x become? A. Right? I mean, it's kind of a weird, dumb question. It's almost so easy it's hard because I'm saying, hey, this is x, right? Let x become a. What does x become? A. Right? It's almost trivial, but that's a limit law. It's the 8th one. The 9th one says if you have x to a power and you let x go to a, then that x gets replaced with a and it just becomes a to that power. And then this law says if you have the square root of x and I let x go to a, then I should just get the square root of a. Again, all I'm doing is, it's essentially like replacing the x with a, right? That's what I'm doing there. And the last law, I'm going to skip that for now. We'll come back to that. All right. I know that that's all probably a little bit like fuzzy to you, and it's okay. I see everyone copying all these things down. You don't have to copy these. These are in your notes. Direct substitution property. Some preliminary information before we get to this property. All right, when we were in pre-cal, when we were in college algebra, and we were dealing with functions, there's something called the implied domain that you may or may not have heard a lot. So I want to remind you what it is when we talk about something called the implied domain. So I'm going to look at this function right here. Okay, the function f of x equals square root of x over x minus 4. Now, if I ask you for the domain of this function, or the implied domain, what I'm saying is, tell me what values of x you are allowed to plug into this function, because there's some you can't, right? So either tell me what I can plug in, or tell me what I cannot plug in. Now, I've already written the answer over there, but let's think about it. Can anyone just look at this and give me a value of x that is not allowed? 4, right? Can't plug in 4. Why? You get 0 on the bottom, right? So we know right now x can't be 4. All right, that's one thing we know. And then what else do we know? Well, we have a square root, don't we? And you can't take a square root of a negative number. Can you take square root of 0? Yes. Square root of 0 is 0. You can take square roots of positive numbers, but you cannot take the square root of a negative number, or else you get into what? Imaginary numbers? And we don't deal with imaginary numbers. In all of your calculus, if you take Cal 1, Cal 2, Cal 3, you'll never see an imaginary number. That's a different class, all right? So imaginary numbers are off the table here. So we can't have imaginary numbers, so we got to make sure that this x is always not negative, right? So how do we say not negative? We say that x has to be greater than or equal to 0. That's how we say it, right? So when somebody puts a function on the board like this, they may not write this down. This may not be explicitly given to you. But you need to know that every function has an implied domain. That there is a domain, even though it's not written, it's implied, right? It's implied that there is some restrictions on x, some things you can't plug in. So this is the notation I used. This is called set notation. So let me explain what this set notation, how this is read. This brace says, okay, we have a set. And what is this set? What's in this set? It's like a bucket, okay? What's in the bucket? What's in the bucket are these values of x. And these values of x are elements of the real numbers. So they're basically numbers on the number line, okay? So I've got this bucket, and inside the bucket are numbers that are in the number line, that are on the number line. And then I have a colon. The colon means such that. Okay, that's what that means. This means element of. Such that what? Two conditions have to be held. The x's that we're talking about have to be greater than or equal to 0. And x cannot be 4. Okay, so I've got this bucket. Inside of it, I've got numbers that come from the real number line, but I have this exception that I have to have numbers that are greater than or equal to 0 and not equal to 4, right? I'm not going to be real hardcore about you using proper set notation. If you want to, great. I'm more concerned, can you just at least give me these restrictions, right? Questions? You sure? Y'all are so quiet, come on. Every function has an implied domain. Every function has an implied domain. Some functions don't have restrictions. Like, for example, how about this function? Are there any numbers you can't plug in here? All right, you can plug any number you want in there. Positive, negative, 0, everything can go in there, right? So what's the implied domain here? All real numbers, right? So how could you say all real numbers? You could say double script R. You could write that, and that would imply all real numbers. Or if you want to use interval notation, you could say negative infinity to infinity, right? Something like that. That's all the numbers between negative infinity and infinity. If you use set builder, it'd be like this. X element R. That's it. Because there's no restrictions. It's just any number you want. All right, got it? Every function has an implied domain. Now, why do we need that? Because of the next very, very important property of limits, right? The whole idea here is to talk about limits. So I gave you all these limit laws. You're scratching your head going, what in the world is this? What have I signed up for here? We're talking about domains now. What the hell's going on? All right, we're just leading up to this right here, the direct substitution property. So here's what the property says. If your function that we're talking about, that we're trying to figure out this limit for, if that function is a polynomial function, which is college algebra, right? Polynomial functions. Rational functions, college algebra. You studied rational functions, right? Trigonometric functions, pre-cal, right? You studied trig functions, sine, cosine, tangent, cotangent, secant, all those functions, right? An exponential function, college algebra. Logarithmic function, college algebra, right? Basically what this is saying is all the functions you've studied up to this point, if that's what we're looking at, then as long as the a that we're approaching, right? X is approaching some number a in a limit. As long as that number a that we're approaching is in the implied domain, as long as that number is actually allowed to be plugged into that function, there's no problems with it, then the limit will always be just what you get when you plug a into the function. Like there's nothing crazy ever going to happen. You have to see an example, all right? Let me show you an example. So as an example of this, let's take the limit as x approaches 2 of x squared plus 1 over x plus 1. So here's what I'm asking you. I want you to try and visualize this too. That's a function, right? This is a function from college algebra. This is a rational function from college algebra. It has a graph, doesn't it? Whatever it looks like, yes? And I'm trying to imagine that if you graphed it, and I don't know what that looks like, but I'm trying to figure out what happens as I approach 2. And I don't know what the graph is, do I? I don't. But I'm trying to figure out, does it go to the same place from both sides? That's what this is asking, right? Well, let's look at this property. Is that a function from before? Is that a rational function? Yeah, right? It is, okay. Can you plug this number 2 into that function without any problems? Are you going to get any like division by 0 or square roots of negative numbers? Are you going to have any issues? No, right? What happens if you plug 2 into the top? 2 squared, 4 plus 1, you get 5 on top, right? And what do you get on the bottom? 3. That's fine, right? The direct substitution property says that as long as this number is in the implied domain without any issues, then the answer to what the limit is just what you get when you plug that number into the function. So just directly substitute 2 in. Plug 2 in, right? 2 goes in here, 2 goes in there. Directly substitute it in, and you get 5/3, and that is our answer. Isn't that nice? So I'm going to do something for you just so you can see. Y'all are worrying me. Okay, x squared plus 1. Divide that by x plus 1. Right? This is the graph of that function, which is not really relevant here, other than the fact that I want us to approach 2, right? Let's go to 2. So let me zoom in on this. We were approaching 2, weren't we? So we're trying to go to 2 from both sides. So let's go up here and let's see. We're coming in here and we're coming in here. From both sides, does it look like we're headed to the same place? Okay, can you tell what value that's headed towards? Something over here, right? I don't know. What is it? 5/3. It's exactly 5/3. All right? And that's because 2 is in the domain of this function, we know that that dot's solid and it comes into that dot from both sides. Got it? That only works if that a is in the domain. Let's do one more. Do one more example here. How about this one? That one's too similar. I guess we could do it. With that one right there. It's very similar to the one we just did, but look at that. Is that a rational function? Yes. Yeah, I mean, it's a function we've dealt with in the past, right? So we look at where we're headed. What is x approaching here? 1. Okay, so we just have to check to make sure. Can we plug 1 in there without any issues? Yeah, right? 1 squared plus 1 plus 2. So the top goes where? 4, and the bottom goes to 2, and 4 divided by 2 is 2, and we are done. The answer is 2. Not too bad, no? Okay, this is not what this class is about, all right? This is the easy case. We always want to look at this first. If we can do a direct substitution, we do a direct substitution. Like this. Let's look at our next example. Is that a rational function?
Yes.
Yes? Okay. Hold on, time out, pause. But it's still a rational function though, right? But there's a domain problem, right? Okay, pause, time out, time out. I want to talk about something real fast. Clear your mind for a second. I'm going to put two functions on the board here. The function f and the function g. I want you to think about what the graphs of those look like. So if we graphed f, what would it be? Straight line where? Horizontal line, up 1 unit, right? Just go up 1, draw a horizontal line. That would be the graph of f, right? Okay, what about g? What happens if you... I have a cat. Oh, there it is. What about g? I mean, here, no matter what value you plug in for x, it always spits out 1, doesn't it? What about g? Same sort of thing, right? You plug in 1, 1 over 1 is 1. You plug in 2, 2 over 2 is 1. 3, 3 over 3 is 1. So this graph looks very similar to this graph. Are they exactly the same, though? Are these the same graphs? They would be? So x over x should always be 1, right? So I should have 1 out this way all the time.